Welcome, my dear learners, for this course on tribology. In our previous lecture, we have discussed hydrodynamic journal bearing, wherein which I have explained the pressure development mechanism in hydrodynamic journal bearing, and also discussed about Petrov's equation, that is lightly loaded journal bearing, and also a derived expression for Reynolds equation in 2 dimension. Recollecting the formulas of Petrov's equation, that is coefficient of friction for bearings in which the load acting on the journal is very small and the journal is rotating at very high speed, and the lubricant used has very high viscosity, for which the eccentricity can be neglected. Such bearings are termed as lightly loaded bearings. For lightly loaded bearings, we can use Petrov's equation to determine coefficient of friction. In today's lecture, let us address numerical problems on lightly loaded bearings, wherein which we can use Petrov's equation to determine coefficient of friction of the lubricant oil. Moving ahead, the problem number 1 of our discussion on problems on lightly loaded journal bearing states that a full journal bearing have the following specifications. Shaft diameter is 45 mm, bearing length is 65 mm, radial clearance ratio is 0.0015, speed is 2800 rpm, that is journal speed. Radial load is 800 Newton. Viscosity of the lubricant is 8.27 into 10 to the power of minus 3 pascals second. The bearing is lightly loaded. Determine frictional torque at the shaft, coefficient of friction, and power loss. So this question was asked in VTU examination in the year 2021. Let us solve this problem. If I list out the data given for problem number 1. So if I list out the data given for problem number 1, we have a full journal bearing having following specifications. Shaft diameter, so diameter of the shaft is given as 45 mm, bearing length is 65 millimeters, radial clearance ratio is also equal to diametrical clearance ratio, which is denoted by xi, which I have clearly explained in our previous lecture, wherein which I have provided the link to go through the Petrov's equation derivation, where I have discussed the diametrical clearance ratio, which is also equal to radial clearance ratio. So diametrical clearance ratio is defined as diametrical clearance divided by diameter, which is also equal to radial clearance by radius. How much is that? That is 0.0015. The speed of the journal is specified as 2800 rpm. The radial load W is given as 800 newtons. The viscosity of the oil eta is given as 8.27 into 10 to the power of minus 3 pascals second. He has clearly specified the bearing is lightly loaded. So I can use Petrov's equation to find coefficient of friction. First, calculate frictional torque. He is asking us to calculate frictional torque. Second, he is asking us to calculate coefficient of friction. And third one, he is asking us to calculate power loss. Power loss due to friction. Now, I am using Design Data Handbook written by K. Lingaya to solve numerical problems. And one more important note is that always the unit of viscosity should be in pascal second. What are the other possible units that he can give us, to confuse are, he can give us in poise, so units of viscosity, that is units of absolute or dynamic viscosity. Absolute viscosity, unit of absolute viscosity. Always I want it in pascal second. So one thing he can give it in poise. 1 poise is equal to 10 to the power of minus 1 pascals a second. If he has given the value as 8.27 poise, then I should have taken it as 8.27 into 10 to the power of minus 1 pascal second. Second one he can give us in centipoise, which is denoted as Cp. Cp stands for centipoise. So centi is already known, centimeter, centi. Centi stands for 10 to the power of minus 2, and for poise I have 10 to the power of minus 1. 10 to the power of minus 2 into 10 to the power of minus 1 will give us 10 to the power of minus 3. So 1 centipoise is equal to 10 to the power of minus 3 Pascal second. Or you can also write it as millipascal second. 1 centipoise is equal to 1 millipascal second. And one more very important one is Reynolds. 1 Reynolds. 1 Reynolds. 1 Reynolds is equal to 6896 Pascal second. 6896 Pascals second. So this is also a very important note to be remembered. 1 Reynolds is equal to 6896 Pascal second. So kindly make a note of viscosities, which is very important to solve numerical problems. Now let us solve problem number 1. If I move for solution, if you carefully observe, he has specified only load acting and he has given diameter and length. Now we know that the pressure acting on the journal is given by load divided by projected area. Load divided by projected area, which can be viewed in our data handbook written by K. Lingaya, referring to page number 23.13, figure 23.6. You can see the projected area, where you can clearly observe that pressure is given by load divided by projected area, L into D. Right, so therefore what is the bearing pressure? So therefore bearing pressure will become, load is 800 newtons divided by length is 45 into diameter is, length is 65 and diameter is 45. Length is 65 millimeters and diameter is 45 millimeters. So therefore I will end up with 800 divided by 65 into 45, which is turning out to be 0.2735 Newton per millimeter square, which is nothing but megapascals. 0.2735 into 10 to the power of minus 6 pascals or Newton per millimeter square. We got bearing pressure. Now, as I said, since it is lightly loaded bearing, you can see here he has clearly specified the bearing is lightly loaded. So therefore I can use Petrov's equation to determine coefficient of friction. Correct? So therefore recall Petrov's equation. So coefficient of friction can be determined by using Petrov's equation. So therefore mu from Petrov's equation is given by 2 pi square of eta n dash by p into 1 by xi. So this is nothing but equation number 23.21. This is equation 23.21 of our design data handbook written by K. Lingaya. This equation is what we have derived in our previous lecture. That is, I have provided the link to go through it. Now let me write it properly. Here coefficient of friction mu from Petrov's equation, because the bearing is lightly loaded. Eta should be in Pascal second, n dash should be in RPS. N is in RPM, I should write in RPS, and P should be in pascals. It should not be in megapascals. So therefore I should write it as 0.2735 in 10 to the power of 6. So if I substitute the values which he has given for us, I have 2 pi square. Eta is the viscosity. E himself has been given in Pascal second. So directly we can use that. It is 8.27 into 10 to the power of minus 3. N dash, that is speed of the journaling, revolutions per second, RPS. So I specified it in RPM divided by 60. That is 2800 divided by 60, which is 46.667. 46.667 divided by bearing pressure, which we have already calculated, that is 0.2735 35 into 10 to the power of 6. This should be multiplied by 1 by diametrical clearance, which is also equal to radial clearance ratio. Diametrical clearance ratio is also equal to radial clearance ratio, which is 0.0015. 0.0015 clearance ratio. Hence, if I solve, I will get coefficient of friction, which is turning out to be 8.27 into 10 to the power of minus 3 into 2800 by 60, that is divided by 0.2735 into 10 to the power of 6, which is again multiplied by 1 by xi. Xi is 0.0015. So I'll get the answer as coefficient of friction is equal to 0.018569. 0.018569 is the coefficient of friction. Now we know that coefficient of friction mu is equal to frictional force divided by load applied. Correct? So therefore, how much is frictional force? Frictional force F mu will be how much? Load times the coefficient of friction. Load is already known, which is 800 Newton. So therefore, it is mu times W, that is 0.018569 times W is 800. Therefore, frictional force is 14.8552 newtons. I got frictional force. Now I can find what is the frictional torque. So we know that frictional torque is equal to frictional force into radius. Torque is equal to force times the radius. So therefore, F mu times d by 2. So how much will you get? Torque, frictional force is known, diameter is also known, that is 45 mm. So therefore, I will get the answer as this into 45 by 2, that is 334.242 Newton millimeters. Second one, that is coefficient of friction, which we have already calculated by using Petrov's equation, which is turning out to be 0.018569. Coefficient of friction is unitless, that is a dimensionless quantity. Next, moving for third one, that is power loss. So general formula for power is force times the velocity. Here we have power loss. So power is lost because of friction. Therefore I should use frictional force. So hence power loss is nothing but frictional force times the velocity. Now how much is velocity? Velocity is pi dn by 60,000. This you people already know. Pi dn by 60,000. We have pi times diameter is 45 mm, speed is 2800 rpm divided by 60,000, which is turning out to be 6.597 meters per second. 6.597 meters per second. Frictional force is already known to us, 14.8552 newtons. So if I multiply these two, I will get power loss. So how much is power loss? Power loss will be 14.8552 into 6.597. So power loss will be 14.8552 into 6.597, which is nothing but 98 watts or 0.098 watts. So this is the solution for problem number 1. Let me pause this video for a while so that you people can copy it down. Later we will address problem number 2. Now moving ahead for problem number 2, which states that a lightly loaded journal bearing has the following specifications: shaft diameter 60 mm, bearing length 80 mm, radial load 1 kN, radial clearance 0.05 mm, oil used SAE 60 at a temperature of 65 degrees Celsius. Coefficient of friction of the bearing under the condition was found to be 0.042. Determine speed of the journal and power loss. Let us solve problem number 2. If I list out the data given for us in problem number 2, we have a lightly loaded journal bearing with shaft diameter, journal diameter of 60 mm, bearing length is 80 mm, radial load W is 1 kN, that is 1000 newtons, radial clearance, it is not clearance ratio, it is just clearance, that is 0.05 mm. Oil used is SAE 60 at operating temperature of 60 degrees Celsius. 65 degrees Celsius. At operating temperature of 65 degrees Celsius. Coefficient of friction mu is 0.042. Is 0.042. Determine speed and power loss. Determine speed and power loss. Let us solve this problem. We know load, we know length, and we know diameter. Thereby I can find the bearing pressure. You are correct. I can find the bearing pressure. So therefore what I will get bearing pressure as load divided by projected area. It is L into D, which I discussed just now in our problem number 1. So load is 1000 divided by 60 into 80, which is nothing but 0.2083 megapascals or Newton per millimeter square. Now we have specified the oil characteristic, that is SAE 60 oil. So therefore, from referring to our data handbook written by K. Lingaya, from page number 23.8, from page number 23.8, refer table number 23.1. Refer table 23.1. For oil characteristics of SAE 60, oil number is, for oil characteristics of SAE 60, oil number will be H. Oil number is H. So now referring to page 23.6, referring to page 23.6 and figure 23.2a, figure 23.2a, we have a graph of absolute viscosity in centipoise versus temperature. That is, we have a graph like this: absolute viscosity in centipoise versus temperature, that is operating temperature. Here we have centipoise. What is this? Eta. This is operating temperature, right? So in this we have different oil numbers A, B, C, D, E, F, G, H, like that, but we want H. So take oil number H. Operating temperature is specified as 65 degrees Celsius. So mark 65 degrees Celsius. So move up like this and intersect oil number H and come horizontally and read the value. So if you read the value, we'll get the answer as 60 centipoise. Eta unit is centipoise. So therefore, from the figure, the viscosity of oil eta is turning out to be 60 centipoise. Just now I explained how to convert centipoise to Pascal second, that is 10 to the power of minus 3 Pascal second. Therefore, eta is 60 into 10 to the power of minus 3 Pascal second. We got viscosity also. Now if you observe, we have all the values of coefficient of friction of Petrov's equation. We know pressure, we know eta. The only unknown is n dash, right? Now I can find what is the n dash by using Petrov's equation, correct? So before moving ahead, I want diametrical clearance ratio, but he has given radial clearance, and you people already know that diametrical clearance ratio xi is equal to diametrical clearance divided by diameter, or it is also equal to radial clearance by radius, right? Here he has given radial clearance divided by radius. So therefore, how much you will get xi as 0.05 is the radial clearance divided by radius. Radius is 30 mm. Because diameter is 60, hence radius will be 30. So therefore, the diametrical clearance ratio, which is also equal to radius clearance ratio, which is turning out to be 1.6667 into 10 to the power of minus 3, and it is dimensionless quantity. I got 1.6667 into 10 to the power of minus 3. Now make use of Petrov's equation. Because he has given the value of mu, hint is that I should use equation of mu. There I can get one unknown. So recollecting Petrov's equation, because it is lightly loaded bearing, we have Petrov's equation given by mu is equal to 2 pi square eta n dash by p into 1 by xi. This is equation number 23.21. This Petrov's equation to calculate coefficient of friction holds good only for lightly loaded bearings. Kindly keep that in mind. Now we know all the values, substitute and simplify. Mu is known, 0.042 given. This is equal to 2 pi square. Eta is 60 into 10 to the power of minus 3. 60 into 10 to the power of minus 3 into n dash is unknown, divided by bearing pressure. I should substitute in pascals. So therefore it is 0.2083 into 10 to the power of 6 pascals. This is multiplied by 1 by xi. How much is xi? Xi is 1.667 into 10 to the power of minus 3. 1.667 into 10 to the power of minus 3. So if I solve, I will get n dash, that is in RPS, as 0.042 into 1.667 into 10 to the power of minus 3 into 0.2083 into 10 to the power of 6. This must be divided by 2 into pi square into 60 into 10 to the power of minus 3. So I'll get n dash as 12.314 RPS. 12.314 RPS. So how much is n? N is n dash into 60, that is I'll get 738.8 RPM. I got 738.829 RPM. Now I can find velocity, because u is pi dn by 60,000. Pi dn by 60,000 will get pi into diameter is 60 into n is 738.829 divided by 60,000. So speed is 2.321 meters per second. We got speed is 738.829 RPM and velocity is 2.321 meters per second. Second one, power loss. Now to find power loss, I want frictional force. We know that mu is equal to frictional force by load. Hence, how much is frictional force? How much is frictional force? Coefficient of friction is given 0.042. Load is specified 1000. Hence, frictional force is 42 newtons. So therefore, power loss is F mu into U. F mu is 42 into U is 2.321. Power loss is 97.482 watts, or it is also equal to 0.097 kilowatts. So this is the solution for problem number 2. Let me pause this video for a while so that you people can copy it down. Later we will address the final problem of today's lecture, that is problem number 3. Now moving ahead for the final problem. Problem number 3 states that a lightly loaded journal bearing has the following specifications. Journal diameter 70 mm, bearing length 55 mm, diametrical clearance is 0.01, speed is 22,000 RPM, radial load is 1 kN. The power loss in the bearing is found to be 3.5 kilowatts. Determine viscosity of oil, coefficient of friction at operating conditions. Let us list out the data given for problem number 3. We have a lightly loaded journal bearing with journal diameter. How much is journal diameter? 70 mm. And bearing length is 55 mm. Diametrical clearance, it is not diametrical clearance ratio. Xi is diametrical clearance ratio, but he has given diametrical clearance, that is C, which is 0.01 mm. Speed, capital N, is 22,000 RPM. Radial load W is 1 kilonewton, that is 1000 newtons. Power loss is specified for us. How much is power loss? 3.5 kilowatts. Very high. So there is a power loss of 3.5 kilowatts. So this is equal to how much? 3.5 into 1000, that is 3500 watts is the power loss. Now he is asking us to calculate viscosity of oil and coefficient of friction. Calculate viscosity and coefficient of friction. Since the bearing is lightly loaded, I can use Petrov's equation. Now if you observe, he has given power loss. So make use of power loss, you will get one unknown. Power loss is frictional force into velocity. Since RPM is specified and diameter is specified, I can find velocity. So therefore unknown what I will get is frictional force. So make use of power loss equation and calculate frictional force. That is the first hint I am getting. Since load is known, length and diameters are known, find out bearing pressure. So what is the formula for bearing pressure? Bearing pressure is given by load divided by projected area. Load is how much? 1000 divided by projected area is 55 into 70. How much you will get? 1000 divided by 55 into 70, which is 0.25974 megapascals or Newton per millimeter square. Now since power loss is specified, I can find frictional force, before which I will calculate the velocity or speed, which is given by pi dn by 60,000. So it is pi times diameter is 70, speed is 22,000 divided by 60,000. How much you will get? Pi times 70 into 22,000 divided by 60,000. That is 80.634. 80.634 meters per second is the speed of the journal or velocity of the journal. Now make use of power loss equation. We know that power loss is equal to F mu into U, force into velocity. Power loss is 3500 watts. Frictional force is unknown. U is 80.634. So therefore you will get frictional force in newtons. How much is frictional force in newtons? 3500 divided by 80.634. That is 43.406 newtons. This is the frictional force. Now we know that coefficient of friction is defined as frictional force divided by normal load. So hence I will get coefficient of friction mu as frictional force divided by normal load. So mu will become this divided by 1000, right? Because load is 1 kilonewton, 1000, which is nothing but 0.0434. 0.0434 is the coefficient of friction. Since the bearing is lightly loaded, I can make use of Petrov's equation for lightly loaded bearings. So one unknown we got, that is coefficient of friction obtained. Now use Petrov's equation for lightly loaded bearings. Mu is equal to 2 pi square eta n dash by p into 1 by xi. This is equation number 23.21. Here what is the unknown? Xi is unknown. We have diametrical clearance. I want diametrical clearance ratio. Diametrical clearance ratio is given by what? Diametrical clearance divided by diameter or radial clearance by radius. Since diametrical clearance is specified, I will do it as diametrical clearance divided by diameter is 70. 0.01 by 70, which is 1.4286 into 10 to the power of minus 4. 1.4286 into 10 to the power of minus 4 is the diametrical clearance ratio. Now substitute all the values, get me the viscosity of the oil, eta. So mu, how much is mu? 0.0434. This must be equal to 2 pi square. Eta is unknown. How much is n dash? N dash is how much? N is 22,000. Therefore n dash will be n by 60. RPS n by 60, that is 22,000 divided by 60, which is 366.667. 366.667. N dash should be in RPS, revolutions per second. This is in RPM. Divide this by 60, you will get N dash. This divided by bearing pressure should be in Pascal. So therefore I should substitute it as 0.25974 into 10 to the power of 6 into 1 by Z, 1.4286 into 10 to the power of minus 4. So if I solve, I will get the viscosity of oil. That is 0.0434 into 0.25974 into 10 to the power of 6 into 1.4286 into 10 to the power of minus 4 whole divided by 2 pi square into 366.667. I'll get the answer as 2.225 into 10 to the power of minus 4 pascals second. The viscosity of oil is 2.225 into 10 to the power of minus 4 pascal second. And coefficient of friction, which we have already calculated, 0.0434. Mu is 0.0434. So this is the complete solution for problem number 3. This completes our discussion on lightly loaded journal bearings. That's all from this lecture. Thank you all.